Thank you for the introduction. So this work, Encore, was done as a collaboration between Xiang Institute and the Robotics Institute at CMU with my collaborators Stelian, Coros, Jennifer Mankoff, and Scott Hudson. So we all love 3D printing. It's great because it allows us to bring the virtual characters to life from the virtual world to the physical world by designing and fabricating them using 3D printers. But the problem is, if, say, I want to extend this minion design to a keychain, there's really no easy way to do it except I have to reprint the entire object. So having to reprint whole objects costs extra time and material, and sometimes unnecessarily replaces the objects that might be of personal value to the users. So wouldn't it be great if we can just put the object on the printer and somehow the printer can figure out and then just directly add any extra attachment or design to the object? So the goal is, instead of treating this 3D printing process as a black box and having to restart from zero every time we iterate on design, what we really want is to take this process apart, and we want to feed the existing 3D objects into a design tool and to the 3D printer so that we can incrementally fabricate this object in a closer in the design and fabrication cycle. So to explore this possibility, I developed 3 different techniques: print over, print-to-affix, and print-through, that will allow a user to directly fabricate an attachment onto an existing object. The first technique is print over. The idea is to print new parts directly over an existing object. For example, the user can select the back of this teddy bear's head, and then the system can figure out how to rotate this teddy bear and scaffold it so that, and the printer can first fabricate a connector structure and then the magnet holder. So this will allow us to transform this existing teddy bear toy into something we can stick on the fridge. So how does print over work? We can start by imagining a very simplified scenario in which you want to fabricate a new attachment onto a flat existing object. So this is easy. All you need to do is to raise the extruder to the height of the existing object. But in reality, the cases are much messier. So this is probably what you have. The 2 objects have very arbitrary surfaces. So the idea is we want to fabricate something called a connector, which will try to create a flat surface so that we can fabricate a new attachment. But we have a problem. Even if we try to print this simple connector, it is very likely the extruder will run into the existing object because its surface is unpredictable and arbitrary. So we have collisions. So how can we do to solve this problem? The key idea is we raise the extruder. So it's very simple. We raise the extruder so that it reaches a point there's no collision. We call it a collision-free point. So this is simple, but there's a problem. So if we try to print with the extruder in the mid-air at this collision-free point, we're probably going to get something like this. This is not the flat layers we'll try to fabricate. So what's the solution? And the key insight in this technique is we observe that if you want to have some sort of flat layers with this configuration, all you need to do is just keep printing. So as the layers stack up, they will actually gradually transform and gradually approximate a type of flat surface we try to make in the first place. And that is the connector we try to fabricate. So at this point, you might wonder, so this looks pretty unstable. How well does it attach? So we'll get to that in the evaluation section. So we now have a solution for print over, but we need to check some edge cases. So the first edge case is there's some structure poking out from the print over area. And the problem is now we have to raise the extruder so much that it exceeds the maximum viable drop, which means if we try to print at this point, the layers are probably not going to stick at all onto the existing object. So we don't want this to happen. The second edge case is there is some other parts of the existing object poking into the space above the print over area. And this again will cause collision. And we can tag that by scanning the space above the print over area, looking at the radius of the attachment plus the radius of the extruder, which together sum up to the range of movement of the extruder. So to summarize print over, it starts with the user importing a model of an existing object and then selects attachment point, we call it P. And then the system rotates the object so that P is facing upward, and in its neighborhood, the print over area is relatively flat. And then we raise the extruder to a collision-free point and make sure we double-check that first, it does not exceed the maximum viable job. And the space above the print over area is collision-free. There's something more we need to do in order to perform print over. So now the object, this teddy bear, is rotated to a very outward position. It's probably not going to stand on its own. So we need something called a support structure. So in the print over process, first we print the support structure, and then we print the attachment. The nice thing about this is this support structure will let the user tuck the teddy bear in place, so the user brings the teddy bear to the attaching point. So in this way, we don't have to instrument any sensor on the printer to look for the attachment point. And this visualization in the tool shows the movement of the print head. So the arrow points to where the print head moves out, and the teddy bear goes in, and then the print resumes to fabricate the attachment, the magnet holder. So with print over, we can really explore a wide range of things, such as fabricating an LED casing directly onto a 9-volt battery to make a simple torch. Or if your coffee is too hot, make a handle for an espresso cup. Or something to hang the screwdriver handle with on the tool shelf. And of course, 1 million keychain. So print over directly grows attachments on existing objects from a range of arbitrary locations. The second technique, print-to-affix, the idea is to print new parts separately and affixable to an existing object. So recall our early scenario, we have this attachment and existing object. So print-to-affix prints this connector structure separately so it can be made conform to both the attachment and the existing objects without causing any printability issues, such as you can make this structure conform to the size of this Coke bottle using some Boolean operations between the two objects models. And this way, we can fabricate, for example, the structure that makes this glue-gun stand, or the 4-pack holder for the Red Bulls you need for your deadlights. Or making a tiny trophy for the egg cup. Or making a reusable battery holder using zip ties. So compared to print over, print-to-affix is much simpler because it prints the compliant attachments separately, and then we assemble them later using some external adhesion or fastening mechanisms. The third technique, print through, so it leverages some special structures, the holes in existing objects, to fabricate new parts. So for example, when printing these scissors labels, in the mid-print, I put the scissors onto the partially completed labels, and then resume the print. And when it's finished, this label is naturally bonded to the handle of the scissors without using any external adhesion or fastening. And one key thing for print through is we need to make sure when we insert the object, it doesn't impede the movement of the extruder afterwards. So we use physics simulation to make sure this does not happen, such as this charm doesn't impede the completion of the bracelet. So the printer can finish it after we insert the charm on the bracelet. So print through leverages holes in existing objects, which creates interlocking attachments without requiring any external adhesion or fastening process. So all these techniques are integrated into Encore, a tool that provides a unified workflow, visualization, and support for direct manipulations. The workflow starts from geometric analysis between interaction exploration and this analysis, where the user can specify different design parameters and options. And then we move on to the model generation, including the attachment, the connectors, and the support structures. Finally, we move on to the printing and post-processing process, which involves customized G-code-driven printer operations, plus some external attaching mechanisms. Please refer to our papers for detail of this pipeline. So we use visualization to specifically a heat map to inform the users of their design. So it shows on the left the goodness of the print over positions over the surface of teddy bear. And on the right, it changes the heat map based on the user selection of different goodness criteria of the attaching point. We also use direct manipulations to simplify the design process. So in this case, the user simply draws a partial stroke on the side of the Coke bottle, and the system figures out the cross-section it needs to deal with. And then it also visualizes the goodness of the attaching point around that area. So we're also conducting evaluation, primarily looking at, first, do our techniques save time and material? Are they strong enough when it comes to the output of the printing? So look at time and material saving. We use the Utah teapot as the benchmark. And we use the slicer program, which computes the approximate time material for printing, which allows us to compare between these techniques. And also, we also include the baseline technique, which is printing everything, the object and the attachment in one piece. So let's look at the time-saving aspect. We can see our techniques save time differently based on the different natures, which remove the extra time we need to print everything in one piece. And as material is correlated to the time spent, we can see our techniques also save the material, because it primarily reduces the time you need to fabricate the original object. And to look at the strength, we performed a torture test. We fabricated a simple handle attachment, and then we use a scale trying to fracture the handle, the attachment handle, and we measure the amount of force it required at the point of fracture. So we look at several factors. The first one is curvature, when it comes to print over versus the baseline. So the results show that print over has this trade-off. It's not as strong as printing everything in one piece. And in particular, both techniques suffer from the increase of curvature, because the higher the curvature, the more difficult it is for the attachment to attach to the existing object. We also look at roughness, coarse-grained roughness between print over and the baseline. And it shows that, again, both techniques suffer from the increase of roughness. It doesn't attach as well compared to the smooth surface. And lastly, we look back at the curvature again, primarily for the print-to-affix using strap. And interestingly, we find that because print-to-affix tries to have the attachment compliant to the existing object, it can actually benefit from an increase of curvature, which allows it to grab better onto the existing object. So to summarize, our goal is to break the integrated black box 3D printing process so that we don't want to always start from scratch every time we start a 3D printing job. We want to take the existing object, fit it into design tool and the printer, so we can incrementally extend our designs. So I've shown 3 different techniques to explore this problem: the print over that fabricates objects directly onto one another, a print-to-affix that fabricates new parts separately and then attach them later using external mechanisms, and print-through that leverages holes of existing objects, all integrated into the Encore tool, which provides a unified workflow, visualization, and direct manipulation. So I hope this work can inspire designers, makers to explore a new range of different fabrication possibilities using existing 3D printers. Thank you.
So any questions from the audience? If you raise your hand, and our student volunteer will bring the mic to you.
Hi, that's very nice work. So I have a question about printing attachment. So when you print an attachment for objects, you need a model for the object, right? Then you can do the Boolean method. So can I scan the object in real time? Then when I print this attachment for the object, you can scan it and then print it in a dynamic process?
I think it's technically possible with systems like Kinect Fusion, but we haven't explored this area yet in our current project. It'll be an interesting future direction.
Thank you.
Any other questions from the audience?
Great talk. Valkyrie Savage, UC Berkeley. So all of your examples are these smooth, hard, rigid objects. And what do you think the possibilities are for this technique? Since we do have like flexible filament, like Ninja Flex and all this stuff, do you think it might be possible to apply this to, you know, soft materials and soft objects?
I think it's entirely possible. For example, for Ninja Flex, my immediate reaction is you need to deal with different material properties. Say if you are dealing with PLA versus Ninja Flex, there might be some parameters you play around in order to figure out how to make the print over work in the best way to attach to the soft material to hard material.
Any other questions from the audience?
Thank you for a great talk. I was wondering, how did you strengthen the vertical axles of your prints? Because I saw most of your applications are printed in vertical rather than the horizontal. And then if you print that to vertical directions, it will not that much stable to stand the print header.
So what do you mean by vertical direction not so stable?
So like print through thing was printed in a vertical direction rather than the flat directions. And then you have the gaps between the left and the right. So like the tag was printed in a safe way if you print in the vertical directions.
Oh,
No, horizontal direction, but you stand up because you want to put the additional material to put through.
Right, so you mean it's not if I print the label vertically, it's because the between layer force is weaker, it's not as strong.
Exactly.
So that's a good question, because if you try to print a label flat, if you think about it in your head, it's impossible to insert the scissors into it, because everything is going to go up and there's no point for insertion. And that's a good question. A trade-off we can make is we orient the label so it's in between the vertical and horizontal. And we can optimize for the best possible strength orientational printing, given that we want to insert the scissors in the middle.
Thank you.
So let's thank our speaker once again.